Okay, so in this final section of the final lecture of the intensive course on categories and modules, I'm going to talk about adjoint functors. So I'm going to start with the definition, which will probably seem sort of weird and unmotivated, and then I shall motivate it with a couple of examples. So let C and D be categories, and let I'm going to have a functor f from C to D and a functor g from D to C. So we say f and g are adjoint if there exists a natural isomorphism So natural isomorphism is a natural transformation that has an inverse which is also a natural transformation. Okay, so let's write down the two functors. We have hom in the category C from G length. This goes from D across C to set. Okay, so what's this functor doing? So I take this product here. So have we defined products of categories? I think not. What should I say about this? So product of categories, I think it's fair to say that it is what you think it is. So the objects are just given by taking the product of the underlying sets of objects. So an object of this is just a pair, an object of D and an object of C. And then a morphism is just a pair of morphisms. So a morphism between the objects in D op and a morphism between the objects in C op. So I think that's the only reasonable definition that it could be. Okay, and then what does this thing do? Well, if I take, say, D, C, it's just going to send it to hom G of D, C. So remember that G goes from D to C, so G of little d lives in C, and so it makes sense to talk about this hom set here. Okay, I'm only saying here, of course, what it does on objects. You should also make sure that there's only one reasonable thing to do on morphisms. So I said a natural isomorphism of functors. I better give a second one. So it has the same, between the same source and target, and here it's going to send D, C to hom in D from D to f of C. Okay, again, I'm only saying what it does on the level of objects, but there's only one sort of reasonable option for what it should do on the level of morphisms. And so f and g being adjoint functors says that there's a natural isomorphism between these two functors. In other words, that there's a natural transformation from here to here, and a natural transformation from here to here, such that the composites are the identities. Okay, so there's an obvious sort of asymmetry between f and g. So here I was a little vague, I said they are adjoint. To be more precise, I should say that G is the left adjoint to F. And F is, you kind of guessed it, right adjoint to G. Okay, so for people who work with contravariant functors, these things get quite a bit more confusing, because if f is contravariant, or if f and g are contravariant, then how you should correctly define, deciding which is the left and which is the right adjoint becomes a little bit of a painful decision. But because we never work with contravariant functors, we're happily saved from this problem. Okay, anyway, this is a very formal thing. Maybe you've only recently met natural transformations, so let's sort of try to unpack this definition a little bit. So in particular, for every, say, object D and C, an object of big C, we get a bijection, or bijection of sets, in this case from hom C g of d, comma, c to hom, this is a squiggly arrow, hom in d from d to f of c. Okay, so one way to think about this is to think of it as saying, for every d, to forget all this natural isomorphism business, and just think, for every c and for every d, I've got a bijection between these hom sets, and furthermore, this is in some sense natural. So if I have a morphism from c to c prime, then I get certain morphisms between these things given by composing with stuff, and then some diagram should commute. Well, to give it precisely, you should actually unravel what it means for there to be a natural isomorphism. But very often when people talk about adjoint functors, this is the only thing they'll write down anyway. They'll just give you a bijection here, and then you're supposed to check for yourself that it is actually a natural transformation. Okay. How do you remember, I said G is left and F is right adjoint. How do you remember this? Notice that G is appearing on the left in this thing and F is appearing on the right. So that's sort of how one could try to remember this. Okay, so let's do some examples. Okay, so let's take my categories to be the category of abelian groups and the category of sets. So what's my functor f going to be? It's going to be the forgetful functor. It forgets the group structure. And so what's my g going to be? G is going to be take the free abelian group on. So given a set, there's always a free abelian group on that set. I guess you could think of f as being forget and g as being generate, but maybe that's a bit silly. Okay, and so the claim is that this is a pair of adjoint functors, that g is left adjoint to f and f is right adjoint to g. So the claim, okay, g is left adjoint to f, and f is right adjoint to g. Okay, obviously this is somewhat, these are equivalent statements, so it's a bit clumsy to write it out like this, but never mind, that's what we're doing. Okay, so how do you, let's write out what this means more precisely. So hom in abelian groups from, say, G of, I'm going to call my set S, maybe, or my group gamma, should be the same thing as hom in the category of sets from S to my group gamma. Maybe I'll call my group capital G, maybe that's better. So G is some abelian group.
Maybe F of G on the right hand side, which is the same set, but just to make clear that we're in
Yeah,
sets.
that's a good idea. So F of G. Indeed. So this is G viewed as a set. So people often suppress notation for forgetful functors, but that's not a good idea when I'm introducing these things. So let's write this in carefully. So in other words, it's saying that to give a map from some set S to this sort of group, to give a map from a set to a group, is the same thing as to give a map from the free group on that set to the group.
Abelian.
Free abelian group. So it's the same as to give a map of abelian groups from the free abelian group on that set to the group. Okay, so hopefully you can write down for so an exercise, if this is not already apparent, is to write down such a bijection as here. If this is very clear to you, if this is easy, then the next part of the exercise is to check that this thing actually gives you a natural transformation between these functors. Okay. So this is one example. So I now want to move on to do a slightly more involved example. So let's do this. So this is the tensor hom adjunction. So there are several different versions of this adjunction. There are quite a few different generalities one can state it in, and well, one gets different versions, that's how life goes. The version I'm going to give today is by far, is a long way from being the most general, but it has the advantage of being a little bit simpler. So, let R to R prime be a map of commutative rings. For me, rings always have a 1, and the map should preserve the 1. Okay. So let M be an R module, and let P be an R prime module. Okay, so then we have maps, so R mod and R prime mod. So we have a map in this direction.
No, functor.
Sorry, functor, thank you very much. So this is the category of R modules, the category of R prime modules. So if I have an R prime module, well, I have a map from R to R prime, so I can always just view this as an R module. So I'm going to call this res for restriction of scalars. I think in my head I call it the view as a functor, but that's a bit clumsy to write down. On the other hand, we can also go this way and use
I don't know if this has been done before in Linus lecture.
This viewing as a module over the other ring thing. Okay, so maybe I should just recap that. So let's talk in more detail about what this map does. So supposing I have an R prime module, say suppose it's called P, then in particular, given any element of R prime and any element of P, I can multiply them together and get a new element of P. That's what it really means to be that P is an R prime module. Now, I have here a map from R to R prime. So if I have any element of R, then well, I can just apply this map to get an element of R prime, and then I can multiply by an element of P. So this gives P the natural structure as an R module. If I have, say, maybe if I give this a name, as R, so if A is in R and P is in P, then define A times P to be just R of A times P. With this multiplication, so R of A is in R prime. This multiplication is because P is an R prime module, and then this just naturally makes P into an R module. And we're going to write it as res of P, where res stands for restriction of scalars. Okay, so this is one half of my adjoint pair. I mean, I wrote this out. It took a little while to write out, but I hope that this is not a sort of scary operation, I think. You're really sort of, in some sense, you're making your module simpler, or at least you're making the ring simpler, maybe. Okay, so the map, so I need a map going the other way. What my map here is going to do is it's going to be taking the tensor product. So okay, so what's happening here, this R prime is naturally an R module, and right, because I have a map, I have a ring map here, so I certainly have an action of R and R prime. So if I have an R module, I can tensor it over R with R prime, and I get a new R module. But actually this thing becomes naturally an R prime module, and that goes by, so I need a way to multiply like an action of R prime on this thing, and I just act by multiplying on this right-hand vector. Okay, so this takes an R module and it spits out an R prime module. I'll give a more concrete example with like real and complex numbers shortly, which may clarify things. Okay, so the claim is that these are adjoint functors. So let me write out the, okay, so this tells us we have a certain natural transformation, but let me write out the sort of the easy version, the analogous thing which is analogous to the statement here. So in particular, we get natural maps. Bijections. So how should this go? This should go hom r prime m tensor over r with r prime, comma p equals hom as r modules from m to res of p. Okay, so a very good thing to check is firstly to make sure that everything here makes sense. Indeed, m is an r module, so it lives here. I apply the functor and it becomes an r prime module, and p was already an r prime module, so it makes sense to take hom as r prime modules. On the other hand, if we look on the right-hand side, m was an r module, and this restriction of scalars of p is also an r module, so it makes sense to take this hom. A priori, this is simply given as a bijection of sets, so one can upgrade it a little bit if one wants to. Okay, so
You want to give the map? Or?
yes, I should give a map. So how is this going to work? So if I have,
Maybe on the new Jamboard.
yeah, I'm trying to remember which is the easy direction.
I think from right to left.
Yeah, so if I have a map from m to this restriction of scalars, so let's go, the given, so map little m, little f from m to restriction of scalars of p, then I want to make a map from this tensor product to p, and so what am I going to do? Well, I'm going to, so to specify a map of r prime modules, it's enough to say what to do on generators of this as an r prime module. But if I take things which generate m as an r module, then they'll still generate this tensor product as an r prime module. So it's enough to tell you, it's enough to define this map on generators of m tensor 1. So let me write this more precisely. So given m in n, define, say, g, I'm making a mess of this. So I'm given a little f from m to the restriction of p, and what I want to make is a map from this tensor product to p. So I'm going to define a map from, and I'm just going to send m tensor 1 goes to f of m. So notice that this restriction of scalars as a set, it's like res of p is just the same set as p. All I've done is to change the ring over which it is a module. But as an abelian group, for example, it's really the same thing. Okay, so given any m in m, given any little m in big M, I send m tensor 1 to this thing. This in particular tells me what to do on like m, well, so that's then enough to uniquely determine a map from m tensor r prime to p.
Well, R prime module, because m tensor, say b would be in R prime, then we get to fn times b.
Indeed, yeah, so, sorry, so this determines the map. A unique map of R prime modules. Because if I have an element of R prime, I can multiply on the right. So, and I also multiply on the right here. Okay, so this is one of my bijections. So this is, in some sense, half of this tensor homojunction, but maybe it's the most interesting half. So maybe I'll give so you've been watching quite a lot of hours of videos, so maybe I will give the example at this point. Okay, so for example, so I'm going to take R to be R, in other words, the real numbers. And I'm going to take R prime to be the complex numbers. I think you can guess what the ring map from R to C is. Okay, and suppose, so now I'm given, so M, So in other words, M is a real vector space and P is a complex vector space. And so, sorry, I should say that this guy is left adjoint to this guy, right? Because the tensor is appearing on the left and the res is on the right. So I should make this more precise. Say, rank tensor R prime is left adjoint to res P. Okay. So that became kind of messy, but I hope that it's what is written here is reasonable.
Going to res,
Yep.
and not res P.
Ah, thank you very much. There should be no P here. Okay, so for example, yeah, let's get back to our example. We have the real and complex numbers. We have an R vector space and a C vector space. And so what's this saying? This is saying that to give a map of C vector spaces from the complexification of a real vector space to a complex vector space P is just the same thing as to give a map of real vector spaces from M to this P viewed, this complex vector space P, but viewed as an R module, so with the natural R module structure. Okay, so hopefully, in this case, so in general the map was somewhat sketchily given, but hopefully in this special case then this can be made more concrete, so it's a good idea to really write out very explicitly what happens here and to convince yourself that there really is a natural bijection in this case. Okay. So I think I should do one more thing by way of motivation, which is to discuss a little bit about how adjoints and limits play with each other. So we spent a long time defining limits and colimits, and then we switched to this apparently very different topic about adjoints, and so it seems a good idea just to quickly say how these connect to each other. Or at least one relationship between these things. Adjoints and colimits commute. So this seems somehow a little bit magical because, in Rob's lecture he talked about exact functors. So the idea is that if you have a functor and you apply it to an exact sequence, if you have a functor from like R mod to, so you have an automorphism of R mod, and you apply it to an exact sequence, this sequence may or may not stay exact, or it may stay left exact but not stay completely exact, or whatever. And so this is sort of a general kind of question one can ask. If you have a functor and then some property of a morphism or whatever, is this property preserved by your functor? So one special but not that special case of this is to look at whether functors preserve limits or whether they preserve colimits. So let's write this down. So if we have, so let f from C to D be a functor, and let I be a shape category, and f from I to C a diagram, which you will hopefully remember from the previous video is just a fancy way of saying f is a functor from I to C. So then we can look at colimit of f, or we can look at, so colimit of f, if it exists, lives in C, and so we can then apply f to it. Alternatively, we can take little f composed with capital F. So little f composed with capital F is then a functor that goes from I to C and then C to D, so it's a functor from I to D. We can take the colimit of this thing. And these are both objects of D. We can do things more carefully and see them as cones in D over the relevant diagrams, but in any case, if nothing else, they're at least objects of D. When are they equal? Or maybe the correct question is, when do they come with a network isomorphism between them? In general, you sort of have no idea. Like, it can happen that this one exists and this one doesn't exist, or that this exists and this doesn't exist, or that they both exist and they're not equal. Like, almost sort of any bad scenario you can think of can happen. But it turns out that when our functor little f has an adjoint, then suddenly everything is much better behaved. So let me state this more precisely. So suppose the colimit of f exists, then, and suppose that f has a right adjoint. So then the colimit of f composed with capital F exists, and these two things are equal. So let me write this out. F of colimit okay, so the simple, like, we haven't said anything about what the right adjoint to f is. It could be anything at all. But just the fact that this adjoint exists is enough to guarantee that f preserves colimits in this sense. So there's a directly analogous statement for limits. Say G from D to C is the right adjoint to F. Sorry, to little f. And let a capital G from I to D be a diagram of shape I. So then, if the limit of G exists, then so does the limit of little g composed with big G, and again, the corresponding things are equal. So G of the limit of big G is equal to the limit Okay, so the proof is easy and the details are given in the notes. Should I state the proof? I think, how long is this segment been? Is it getting long?
You can just refer to the notes, right? So.
Yeah, I think this segment's getting a bit long, so I'm not going to give the proof in detail. It's given in detail in the notes. So I will just conclude by briefly saying sort of why is this kind of thing useful. So understanding when functors preserve limits and colimits is a sort of very basic thing. It's related to, so understanding when functors preserve injective maps, for example, this is a special case of, or a variant on this, deciding when functors are left exact that Rob talked about at some length. But also, if you have, you know, if one example of colimits is gluing together topological spaces along open subsets. So if you have some functor from top to another category, it's very useful to know if your functor behaves well with respect to gluing together topological spaces. That's exactly the kind of question that asking whether a functor preserves limits or colimits is asking. And so just knowing the existence in a very abstract sense of adjoints, either left or right, will give you these kind of conclusions completely formally. So for example, we had this adjunction between the forgetful functor and the free functor between abelian groups and sets. Then that tells you things about the limits and colimits being preserved by these two functors. Okay, again, there are more details in the notes, but maybe I will stop now, concluding the last one.